Okay, so for problem number 10, this is a challenge problem. We've got a positive charge Q right at the center, and we've got negative Q, which is uniformly distributed throughout the spherical volume. So as you go out, you enclose more and more negative charges. Determine the electric field outside the sphere at a distance from the center. Again, anytime we're outside of a sphere, we can treat it as a point charge, but we have to think about the charge enclosed. A positive Q and a negative Q enclosed in that Gaussian surface is going to give me an electric field, an enclosed charge of 0. So when I use KQ over R squared, the Q is 0, which means the electric field is also 0. Okay, the next one is determine the potential outside the sphere at a distance R greater than R. So in this scenario, if we're trying to find a potential at that surface, we have the change in potential from infinity to R, which is VR minus V infinity, is equal to the negative integral from infinity to R of E dot dr. But I'm going to replace this E with a 0, because that's what my electric field is. And the integral of 0 is just 0. And the potential at infinity is also equal to 0. So the potential at R is equal to 0. And the unit for that would be volts. The unit for electric field is newtons per coulomb. Okay, let's do part C, where we actually have to think about the electric field inside the sphere at a distance R less than R from the center. So now we are looking at the electric field here, where we've got a positive Q enclosed in the center and we have some negative Q enclosed depending on the radius. So I'm going to start with my Gauss's law. The enclosed integral of EdA is equal to Q enclosed over epsilon naught. And this is a challenge problem, so I do encourage you to do it because the concepts are still very similar to what we're doing in class, but this is a pretty unique problem with the positive Q and the negative Q uniform distribution. So if you can do this, then you should be very comfortable with anything you see on a test. Okay, so the enclosed integral of EdA is our Gaussian surface, so it's E times 4 pi little r squared. Our Q enclosed is the hard part. So I'm going to focus on the negative charge. If it's a uniform charge distribution, then my Q enclosed, if I'm just focused on the negative charge, not the positive, is going to be the charge over the volume, which is 4/3 pi little r cubed, and that's equal to the full negative charge over the full volume, big R cubed. Again, simplify everything down, and you get Q enclosed as negative Q over little r cubed divided by big R cubed. Now, that's not the full charge enclosed. That's just the negative charge enclosed. I still have this positive charge in the center. So when I want the full charge enclosed, I still have to add that positive Q. So the Q enclosed total is positive Q minus Q r cubed over big R cubed. And that whole thing is over epsilon naught. Okay, so I'm going to divide my 4 pi epsilon naught to the other side, and I get an electric field of Q minus Q r cubed over big R cubed divided by 4 pi epsilon naught little r squared. The next step I'm going to do here is because I know I have to find the potential, I'm going to try to condense these little r's together. I also know that this 1 over 4 pi epsilon naught equals k. So I'm going to pull that out. I'm going to pull out my common variable q, and then I've got 1 minus r cubed over big R cubed divided by little r squared. And that actually gives me 1 over r squared and r cubed over big R cubed over r squared. So I can simplify this into kq 1 over r squared minus r over big R cubed, because this r squared reduces with 2 of those, and then it also has to be in the denominator of this guy as well. So when I start working with my potential, which is the next step, that's part D, I can easily integrate this expression with respect to little r when it's written in this fashion. So let's do part D now. Part D is to try to find the potential at some arbitrary distance, little r, when it is inside of the sphere. Now, we have to take the change in potential, and since we already know that the potential at the surface is 0, then we can take the integral from that surface in, and the final potential would be v at little r minus v on the surface big R. This is equal to 0. Then I can plug in my integral from big R to little r, and then I have to plug in the electric field in that region, which is this kq 1 minus r squared, which I'm going to rewrite as r to the negative 2 minus r over r cubed with respect to dr. So I can pull out all of those other constants. Vr is equal to negative kq, and then I can integrate r to the negative 2 as r to the negative 1 over negative 1, which is 1 over r, negative 1 over r. And then I'm going to integrate this guy. It's r to the 1, so I add 1 to that, and divide by 2, and I still leave that r cubed down there. And then I'm going to plug in my limits, big R to little r. So let me just make sure all my signs look okay. So I've got a bunch of negatives. I distribute this negative into each side, and that turns everything into positives. And then I'm going to plug in my limits, which is kq. The first limit is 1 over r plus r squared over 2r cubed. And I'm going to subtract it from 1 over the big R substituted is 1 over big R plus big R squared over 2 big R cubed. And then I can condense a lot of this. This R squared and that R cubed can reduce. I'm going to get common denominators here to combine those two. And I get kq times 1 over little r plus little r squared over 2 big R cubed minus 3 over 2r. And I'm just going to double check my answer, but I do think that is correct. That looks good.